Now you're back to Nebula Nights, where we explore the cosmos through a lens of wonder and relaxation. Tonight, we embark on a thought experiment that pushes the boundaries of imagination while grounding ourselves in solid science. What would happen if Earth suddenly stopped spinning, or if it slowed down gradually over time? This is a journey through hypothetical physics, catastrophic scenarios, and the delicate balance that makes our planet habitable. So settle in, get comfortable, and let your mind wander through these 100 sleepy facts about a world without rotation. Let the gentle rhythm of scientific exploration carry you toward rest as we contemplate the spinning dance that keeps us alive. Fact 1 begins with understanding what we often take for granted. Earth is constantly spinning beneath our feet at remarkable speeds. At the equator, the surface of our planet moves at approximately 1,040 miles per hour, or roughly 1,670 kilometers per hour. This is faster than the speed of sound, yet we feel nothing. No wind in our hair, no sense of motion, because we're moving right along with everything else on this spinning sphere. This rotation isn't arbitrary or random. It's a fundamental characteristic inherited from the very birth of our solar system, roughly 4.6 billion years ago. Back then, a vast cloud of gas and dust began to collapse under its own gravity, and like a figure skater pulling their arms inward, the cloud spun faster and faster as it contracted. This primordial rotation was passed down to everything that formed from that cloud, including our Earth. The rotation has been part of our planet's identity since the moment it coalesced from cosmic debris, and it shapes every aspect of our existence in ways both obvious and subtle. The speed of this rotation varies dramatically depending on where you stand. At the poles, you would complete a tiny circle once per day, rotating at essentially zero velocity relative to Earth's center. But travel to the equator and you're moving at that breakneck 1,000 miles per hour. Someone standing in the middle latitudes, perhaps in New York or Madrid or Tokyo, travels at a more moderate 700 to 800 miles per hour. This gradient in velocity creates forces that shape our planet in profound ways, from the bulge at the equator to the patterns of winds and ocean currents that distribute heat and moisture across the globe. Our planet completes one full rotation every 23 hours, 56 minutes, and 4.09 seconds. This is what astronomers call a sidereal day, the time it takes for Earth to rotate once relative to the distant stars. The familiar 24-hour day we use is actually the time it takes for the Sun to return to the same position in the sky, which is slightly longer because Earth has also moved a bit in its orbit around the Sun during that rotation. These measurements, precise to fractions of seconds, reveal a clockwork universe where nothing truly remains static, where everything dances to the rhythms set in motion billions of years ago. The rotation of Earth creates something called angular momentum, a fundamental property of rotating objects that resists changes in that rotation. Angular momentum depends on three things: the mass of the object, how that mass is distributed, and how fast it's spinning. For Earth, with its mass of nearly 6 trillion kilograms distributed across a sphere with an equatorial radius of 6,378 kilometers, the angular momentum is immense. This is why Earth keeps spinning despite the gradual braking effects of tidal forces. The conservation of angular momentum is one of the fundamental laws of physics, stating that angular momentum cannot be created or destroyed, only transferred from one object to another. Each rotation brings us through the cycle of day and night, a rhythm so fundamental to life on Earth that virtually every organism has evolved to anticipate and respond to it. The alternation between light and darkness drives photosynthesis in plants, triggers the opening and closing of flowers, governs the activity patterns of animals, and regulates the sleep-wake cycles of humans. This daily rhythm penetrates deep into our biology, affecting not just when we sleep, but also when our body temperature peaks and falls, when certain hormones are released, and even when our cells are most actively repairing DNA damage. The rotation creates an apparent motion of the sun across our sky, rising in the east and setting in the west. But of course, the sun isn't moving across our sky at all. We are rotating toward it in the morning and away from it in the evening. This illusion is so convincing that for most of human history, people naturally assumed the sun orbited Earth. It took careful observations and brilliant reasoning to realize that we are the ones in motion, spinning through space while the sun remains relatively fixed in position. This realization, which seems simple now, required overturning centuries of assumption and perception. The spin of Earth also interacts with other celestial bodies, most notably our moon. The gravitational pull of the moon creates tidal bulges in Earth's oceans, raising the water level on the sides of Earth nearest to and farthest from the moon. But because Earth rotates much faster than the moon orbits, these tidal bulges are carried forward by Earth's rotation, leading the moon slightly. The gravitational attraction between the moon and these leading bulges creates a subtle braking force that gradually slows Earth's rotation. This process is incredibly slow, adding only about 1.4 milliseconds to the length of day every century, but over geological time spans, it has been significant. This tidal braking is why days on Earth are getting longer, imperceptibly to humans, but measurably over millions of years. Ancient corals, which grew daily growth rings like trees grow annual rings, reveal that 400 million years ago, a year contained about 400 days, each about 22 hours long. The moon was closer then, orbiting faster, and Earth spun more rapidly. As Earth's rotation has slowed, that angular momentum hasn't disappeared. Instead, it has been transferred to the moon's orbit, causing our lunar companion to gradually spiral away from us at a rate of about 3.8 centimeters per year. The rotation of Earth creates what we call the Coriolis effect, a consequence of the fact that different latitudes move at different speeds. When air or water moves across Earth's surface, particularly over large distances, it appears to curve. In the northern hemisphere, moving objects appear to curve to the right. In the southern hemisphere, they curve to the left. This isn't because any force is pushing them sideways. Rather, it's because the ground beneath them is rotating at different speeds as they move north or south. The Coriolis effect is responsible for the spinning of hurricanes and typhoons, the circulation patterns of ocean currents, and the large-scale patterns of atmospheric circulation that govern our planet's climate. Without this rotation, none of these patterns would exist. The distribution of heat from equator to poles would be entirely different. The trade winds that powered the age of sail would not exist. The great ocean currents like the Gulf Stream that warm Europe would cease. The monsoons that water vast agricultural regions would disappear. The entire climate system, evolved over billions of years to work with a rotating planet, would collapse into something unrecognizable. This rotation, invisible and unfelt in our daily lives, is as essential to Earth's habitability as the atmosphere itself. The rotation also creates a slight flattening of our planet. Earth is not a perfect sphere, but an oblate spheroid, slightly wider at the equator than from pole to pole. The equatorial diameter exceeds the polar diameter by about 42.7 kilometers. This bulge exists because the centrifugal effect of rotation causes material to be pushed outward most strongly at the equator, where the rotational velocity is greatest. If Earth stopped spinning, this bulge would gradually disappear as the planet slowly relaxed into a more perfect sphere under the pull of its own gravity. This equatorial bulge means that Mount Chimborazo in Ecuador, while not the highest mountain above sea level, is actually the farthest point from Earth's center. Its peak sits on the equatorial bulge, placing it about 6,384 kilometers from Earth's core, compared to Mount Everest at only about 6,382 kilometers. If you wanted to be as far as possible from the center of Earth while still standing on its surface, you would climb Chimborazo, not Everest. The rotation of Earth, this simple spinning motion that we never feel, is thus woven into the fundamental fabric of our planet's character. It shapes our climate, drives our weather, creates our daily rhythms, and even affects the very shape of the world. To imagine Earth without this rotation is to imagine a fundamentally alien world, one where almost nothing would work as we know it. As we drift deeper into this thought experiment, as the comfort of your bed embraces you, keep this thought close. The spinning of Earth, invisible and imperceptible, is one of the great gifts of our cosmic circumstance, a motion set in place billions of years ago that continues to make life as we know it possible. Let us now venture into the realm of catastrophe, imagining the unimaginable. Earth's rotation coming to a sudden, complete halt. This scenario violates the laws of physics as we understand them. There is no known natural force that could stop Earth's rotation suddenly. Even the most massive cosmic collision would likely shatter the planet rather than simply stop its spin. But for the sake of our thought experiment, let us imagine that some force beyond nature simply brings our planet's rotation to a standstill in an instant. The consequences would be biblical in scale. The first fact you need to understand about this scenario is that when Earth stops, everything on Earth does not stop with it. This is where Newton's first law of motion becomes terrifyingly relevant. An object in motion tends to stay in motion unless acted upon by an external force. The atmosphere, the oceans, every building, tree, car, and person on the planet is currently moving eastward at speeds that vary from 0 at the poles to over 1,000 miles per hour at the equator. If the solid Earth suddenly stopped spinning, all of these things would continue moving eastward at their current velocities. Imagine standing at the equator when this impossible event occurs. You are currently moving eastward at about 1,040 miles per hour. When Earth stops, you do not. You, along with everything else not firmly attached to bedrock, would be thrown eastward at supersonic speeds. The air itself would become a wind of unimaginable violence, moving at over 1,000 miles per hour, far exceeding the strongest hurricane ever recorded. This wind would not be a gentle breeze that builds up over time. It would be an instantaneous wall of air moving faster than sound, obliterating everything in its path. Buildings would not just collapse, they would be sheared off their foundations and hurled eastward. Steel and concrete, those materials we think of as so solid and permanent, would behave like leaves in a storm. Skyscrapers would topple and tumble, breaking apart as they rolled across the landscape at hundreds of miles per hour. Mountains would partially withstand the initial wind, being made of solid bedrock attached to Earth itself, but their loose rock and soil would be stripped away in seconds. Forests would be flattened instantly, trees snapped off at their bases and carried away like toothpicks. The oceans would become the most terrifying force on the planet. Water, being fluid and having tremendous mass, would continue moving eastward when Earth stopped. At the equator, where the ocean is moving at over 1,000 miles per hour, the water would effectively launch itself off the surface of the planet. Tsunamis don't quite capture what would happen. The entire ocean would become a miles-high wall of water, traveling eastward at supersonic speeds, scouring continents down to bedrock. Even far from the equator, the devastation would be total. At 40 degrees latitude, roughly the latitude of New York, Madrid, or Beijing, the surface velocity is about 780 miles per hour. Everything would still be thrown eastward at speeds that make the fastest racing cars look stationary. The only places that might see any survival would be the immediate vicinity of the poles, where the rotational velocity drops to near zero. But even there, the collateral effects would be catastrophic. The atmosphere itself would become a weapon of unimaginable power. Air moving at 1,000 miles per hour exerts forces measured in tons per square meter. Nothing built by humans could withstand it. The air pressure would pulverize concrete, tear steel, and reduce anything on the surface to rubble. The friction of air moving at such speeds over the ground would generate tremendous heat, potentially igniting widespread fires that would be fanned by winds moving faster than any hurricane. As objects tumbled and flew eastward, they would eventually crash into the sides of mountains, valleys, and other geographic features, moving westward in their reference frame. The kinetic energy involved in these collisions would be released as heat, sound, and destructive force. A car moving at 800 miles per hour and suddenly stopped by collision with a mountain releases energy equivalent to several tons of TNT. Multiply this by every object on Earth's surface, and the total energy release would be comparable to thousands of nuclear weapons detonating simultaneously across the globe. The human toll would be beyond comprehension. At the equator, the deceleration from 1,000 miles per hour to zero, if it occurred over even a few seconds, would subject the human body to forces dozens of times stronger than gravity. Bones would shatter, organs would rupture, and survival would be impossible. Further from the equator, where speeds are lower, people might survive the initial event if they were fortunate enough to be in deep valleys or other protected locations, but they would emerge into a world scoured clean of civilization. In the minutes and hours following this catastrophic stop, secondary effects would continue the destruction. The atmosphere, after its initial mad rush eastward, would begin to seek equilibrium, generating winds of almost equal violence rushing back westward. These return winds would ensure that anything that somehow survived the initial event would likely be destroyed in the aftermath. The oscillations might continue for days, the atmosphere sloshing back and forth around the globe like water in a disturbed bathtub, creating repeated waves of destruction. The heat generated by all this friction and collision would raise atmospheric temperatures dramatically. Some calculations suggest that the friction of the atmosphere alone could raise temperatures by hundreds of degrees in some regions. The oceans, smashing against continents at supersonic speeds, would be partially vaporized by the friction and compression. Vast quantities of water vapor would enter the atmosphere, creating a thick, hot, turbulent cloud layer that would blanket the planet. Earthquakes would shake every tectonic plate as the sudden stop transmitted. Stresses through Earth's crust. The planet's interior would continue rotating for some time, as the inner core and mantle have their own angular momentum and are not rigidly connected to the crust. This would create immense shearing forces at the boundaries between these layers, potentially triggering volcanic eruptions on a scale never seen in human history. Lava would pour from countless new volcanic vents as the pressure and stress on the magma chambers became unbearable. The magnetic field, generated by the motion of molten iron in Earth's outer core, would begin to change immediately. The dynamo effect that maintains our magnetic field depends on the rotation of Earth to organize the convection currents in the core into patterns that generate a dipole magnetic field. Without rotation, these patterns would break down over time. The field would not disappear instantly, as the core has its own momentum and would continue rotating for a while, but it would begin to weaken and become more chaotic within days or weeks. In this scenario of sudden stopping, there would be no survivors to witness the aftermath. The kinetic energy of Earth's rotation, suddenly converted to heat and destructive force, would effectively sterilize the planet's surface. Only life deep in the oceans, far from the surface turbulence, or deep underground in caves and rock formations might survive. Even then, the long-term consequences would likely doom most complex life. The scenario is, mercifully, impossible given the laws of physics that govern our universe. But let's imagine, just for a moment, that somehow, impossibly, you survived. Perhaps you were at one of the poles, where the rotational velocity is essentially zero. Perhaps you were deep underground when the catastrophe struck. You emerge into a world transformed beyond recognition. The landscape is unrecognizable, scoured flat by winds and water. The atmosphere is thick with dust and water vapor, the sky a uniform gray. Temperatures are extreme, swinging wildly as the climate system struggles to find new equilibrium. There is no sound of birds, no buzz of insects, no whisper of leaves in wind because there are no birds, no insects, no trees. The biological world has been erased as thoroughly as if by nuclear fire. The earth is still there, still solid beneath your feet, but it is a dead world now, its motion stolen, its life extinguished. This is the nightmare scenario of sudden stopping, a catastrophe so complete that it barely bears contemplation. Fortunately, as noted, it cannot happen. Earth's rotation is too stable, too protected by the fundamental laws of physics to be stopped suddenly. But understanding this impossible scenario helps us appreciate the alternative. The gradual slowdown scenario, which, while still catastrophic, would at least give life on Earth a chance to adapt. Let that thought ease your mind as you relax deeper into sleep, knowing that Earth's spin is safe, steady, and will continue long after we are all gone. Now let us slow down our thought experiment. Instead of an impossible sudden stop, imagine that Earth's rotation gradually slows over decades or centuries. This gives us time to observe and understand one of the most dramatic consequences: the complete redistribution of Earth's oceans. This scenario, while still catastrophic, is at least physically plausible and gives us a chance to see how deeply Earth's rotation influences the most fundamental geography of our planet. The key to understanding this ocean migration lies in the equatorial bulge we discussed earlier. Currently, Earth's rotation creates a centrifugal effect that pushes water, air, and even the solid surface of the planet outward at the equator. The water at the equator is about 8 kilometers higher, relative to Earth's center, than it would be if Earth were not rotating. This doesn't mean the sea level at the equator is 8 kilometers higher than at the poles, when measured from the surface. Rather, it means the entire surface, including the ocean floor and continents, is pushed outward at the equator. The effect on sea level is more subtle but still dramatic. Sea level at the equator, measured from Earth's center, is about 21 kilometers higher than at the poles. If Earth's rotation slowed and eventually stopped, this equatorial bulge would gradually disappear. The centrifugal force that maintains it would weaken and eventually vanish. When that happens, the 8-kilometer-high bulge of water, currently held at the equator by centrifugal force, would begin to flow toward the poles, where gravity's pull is slightly stronger due to Earth being closer to spherical there. The result would be a massive redistribution of ocean water from the equatorial and mid-latitude regions toward the Arctic and Antarctic. Computer models of this process reveal a stunning transformation of Earth's geography. As the oceans drain away from the equatorial regions, vast new land masses would emerge. A continuous belt of land would encircle the globe along the equator, connecting Africa and South America, spanning the Pacific, and creating a mega-continent that would dominate Earth's new geography. This equatorial supercontinent would be dry, barren, and subject to extreme temperatures. But it would be land, rising from what are currently some of the deepest parts of the Pacific and Atlantic Oceans. Meanwhile, the water fleeing the equator would accumulate at the poles, creating two massive circumpolar oceans. The Arctic Ocean would expand dramatically, drowning everything north of about 45 degrees latitude. All of Canada, Alaska, Siberia, Scandinavia, the British Isles, and the northern portions of Europe and Asia would disappear beneath hundreds of meters of water. Similarly, in the southern hemisphere, the Southern Ocean would expand to cover all of Antarctica and reach well up into the southern portions of South America, Africa, and Australia. The boundary between the equatorial landmass and the polar oceans would become the new coastline of this transformed Earth. This boundary would roughly follow circles of latitude around 45 degrees north and south, though the actual position would vary depending on the existing topography. High mountain ranges like the Himalayas and Andes would remain above water even at higher latitudes, becoming islands in the vast polar seas. The Mediterranean Sea would drain completely, revealing a deep basin. The Caribbean would dry up. The North Sea would expand into a vast gulf, separating what remains of Europe from the new Northern Ocean. This transformation would not happen overnight. If Earth's rotation slowed gradually over, say, 100 years, the ocean redistribution would happen gradually as well. Sea levels at the equator would drop by meters every year, exposing first the continental shelves, then deeper and deeper parts of the ocean floor. Coastal. Cities in equatorial and mid-latitude regions would find themselves increasingly far from the ocean. Miami, Singapore, Mumbai, and Rio de Janeiro would eventually be hundreds of kilometers from any coastline, though long before that point, the changing climate would likely have made them uninhabitable for other reasons. In the higher latitudes, the opposite would occur. Cities like London, New York, Tokyo, and Moscow would watch the ocean levels rise relentlessly year after year. Unlike the slow sea level rise we worry about today from climate change, this would be measured in meters per year. Coastal defenses would be overwhelmed quickly. Entire nations would need to relocate their populations to higher ground or to the emerging equatorial lands. The human migration triggered by this event would be unlike anything in history, with billions of people forced to move as their homelands either dried up or drowned. The volume of water involved in this migration would be staggering. Earth's oceans contain roughly 1.3 billion cubic kilometers of water. In a rotating Earth, this water is spread relatively evenly across the globe, with some accumulation at the equator. In a non-rotating Earth, this same volume of water would be concentrated primarily in two polar oceans. The depth of these polar oceans, particularly in the Arctic, would be immense, potentially reaching depths of several kilometers in the centers of the new ocean basins. The drainage of the equatorial oceans would reveal landscapes never seen by human eyes. The abyssal plains of the Pacific and Atlantic, currently under 4 to 6 kilometers of water, would rise into the sunlight for the first time in hundreds of millions of years. These plains, covered in fine sediment accumulated over eons, would be utterly flat and featureless. The mid-ocean ridges, currently marking the boundaries between tectonic plates, would become mountain ranges marching across the new continents. Seamounts would become hills and mountains. The trenches, like the Mariana Trench, would become the deepest valleys and canyons on the exposed seafloor. This newly exposed land would initially be covered in marine sediment, full of the remains of ancient sea life. Over time, this sediment would dry, crack, and be sculpted by wind and what little rain fell in these equatorial regions. The landscape would be alien and harsh, but it would be land, and eventually, life would colonize it, beginning with microorganisms and eventually progressing to more complex life forms if conditions allowed. The new polar oceans would be dark, cold, and deep. At their centers, sunlight might barely penetrate even the surface layers due to the high latitude and the thickness of sea ice that would form. These oceans would be even more isolated from the sun's warmth than the current polar regions. Life in these oceans would face challenges unlike anything seen in Earth's current oceans. The cold alone would slow metabolism to a crawl. The darkness would eliminate photosynthesis except at the edges. The pressure at the bottom of these deep polar basins would be crushing. The boundary between land and ocean, the new coastline at roughly 45 degrees latitude, would become the most important geographic feature on Earth. This is where the habitable zones would be, where ocean met land, where both terrestrial and marine ecosystems could potentially thrive. But even these regions would face challenges. The climate along these coastlines would be extreme and unpredictable, subject to massive temperature swings and radical weather patterns driven by the new heat distribution on a non-rotating Earth. The redistribution of ocean water would also affect Earth's moment of inertia and therefore the rate at which any remaining rotation decays. As mass moves toward the poles, it gets closer to the rotation axis, which, according to the conservation of angular momentum, would actually cause any remaining rotation to speed up slightly, like a figure skater spinning faster as they pull their arms in. However, the effect would be small and would not significantly change the overall trajectory toward a stopped Earth. Let this image of Earth's transformed oceans accompany you into deeper rest. The water, always seeking its lowest level, flowing from equator to poles, finding new basins to fill, leaving old ones dry. The tide of change measured not in meters but in kilometers, not in years but in decades. A patient, unstoppable transformation driven by the most fundamental forces of nature, gravity and rotation, working in their eternal dance. As you drift towards sleep, imagine those ancient ocean floors drying in the sun for the first time in billions of years, while the far northern lands sink quietly beneath expanding seas. With Earth's rotation slowed to a stop, we enter perhaps the most profound change to our planet's character, the end of the familiar cycle of day and night. For as long as life has existed on Earth, the alternation between daylight and darkness has been the most reliable, most pervasive rhythm governing existence. Every 24 hours, the sun crosses our sky, bringing light and warmth, then disappears beyond the horizon, bringing darkness and cooling. This cycle has been so constant for so long that life is fundamentally structured around it. Without rotation, this cycle would vanish, replaced by something utterly alien. On a non-rotating Earth, the length of a day would equal the length of a year. One full cycle from sunrise to sunrise would take 365.25 current days. Half of Earth would face the sun constantly, locked in permanent daylight, while the other half would face away from the sun constantly, locked in permanent darkness. The only exception would be a narrow band around the terminator, the boundary between the light and dark sides, where the sun would sit perpetually on the horizon, never fully rising or setting. The light side of Earth would experience conditions unimaginable in our current world. The sun would not move across the sky but would hang in one position, slowly drifting as Earth orbited but remaining roughly in the same direction. If you stood at the point directly beneath the sun, called the subsolar point, the sun would be directly overhead every moment of every day. There would be no sunrise, no sunset, no dusk, no dawn. Just an eternal noon, with the sun glaring down from the zenith with unrelenting intensity. The temperature at the subsolar point would climb to deadly levels. With 6 months of continuous sunlight and no night to cool things down, surface temperatures could easily exceed 150 degrees Celsius, hot enough to boil water at lower elevations. The ground itself would heat to temperatures that would be painful to touch within seconds and lethal within minutes. Any water at the surface would evaporate, quickly creating a zone of intense atmospheric convection as hot air rose from the baking ground. The area directly beneath the sun would be a blast furnace, absolutely inimical to life as we know it. Moving away from the subsolar point toward the edges of the daylit hemisphere, conditions would gradually become less extreme. The sun would hang lower in the sky, spreading its energy over a larger area. Temperatures would drop from the hellish conditions at the subsolar point to merely scorching conditions at mid-latitudes. But even these cooler regions of the daylit side would be subjected to relentless heating with no respite. Any moisture would be baked out of the soil over time. Rivers and lakes would evaporate under the constant sun. Only the most heat-adapted organisms might survive in these regions, and even then, they would need special adaptations to cope with the perpetual daylight and heat. The only potentially habitable zones on the daylit hemisphere would be near the terminator, where the sun hangs perpetually at or near the horizon. Here, the sun's rays would strike at a glancing angle, spreading their energy over a large area and creating temperatures that might be tolerable. But the transition zone between the superheated daylit side and the frozen dark side would create extreme atmospheric turbulence, with massive storms and winds that would make these regions challenging for any life. The dark side of Earth would face opposite but equally extreme conditions. With no sunlight reaching this hemisphere for months at a time, temperatures would plummet. The ground would radiate its heat into space with no incoming solar energy to replace it. Temperatures would drop below -100 degrees Celsius in many regions, approaching the frigidity of the lunar surface during lunar night. Any water on the surface would freeze solid. Atmospheres of carbon dioxide and nitrogen would begin to freeze out of the air at the coldest points, creating dry, ice glaciers of frozen atmospheric gases. The only heat sources on the dark side would be the Earth's internal heat and, ironically, some warmth transported from the daylit side by atmospheric and oceanic circulation. But this heat would be inadequate to prevent most of the dark hemisphere from descending into a deep freeze. The polar regions on the dark side, farthest from any potential warming influence from the daylit side, would be the coldest places, potentially rivaling the frigid wastes of Pluto's surface in their hostility to life. In the perpetual darkness, any remaining liquid water would accumulate. Water vapor from the hot daylit side would be transported by winds and ocean currents toward the dark side, where it would freeze out of the atmosphere as snow and ice. Over time, massive ice sheets would build up on the dark hemisphere, potentially kilometers thick. These ice sheets would reflect what little light reached them from the stars, maintaining their frozen state. They would represent a vast reservoir of water, locked away from the heat of the sun, creating a stark divide between the water-rich dark side and the dry daylit side. The terminator, the boundary between perpetual day and perpetual night, would be the most dynamic region on this transformed Earth. Here, the sun would hang at or just below the horizon, creating a zone of twilight that never progresses to full day or full night. This region would experience temperatures midway between the extremes of the two hemispheres. The temperature gradient between the hot daylit side and cold dark side would drive powerful winds along the terminator, creating a band of perpetual storms encircling the globe. In this twilight zone, you might find the only truly habitable regions on a non-rotating Earth. Temperatures would be moderate, neither too hot nor too cold. The sun, hanging at the horizon, would provide some light and warmth, but not the killing heat of perpetual noon. The atmospheric dynamics driven by the temperature differences between the two sides would bring moisture from both sides, creating conditions where liquid water might exist and life might persist. This narrow band, perhaps only a few hundred kilometers wide, would be the refuge for any surviving complex life. Life adapted to our current world, with its reliable day-night cycle, would struggle desperately to survive in this new reality. Plants, which need sunlight for photosynthesis, but also darkness for certain cellular processes, would find the eternal day or eternal night incompatible with their biology. Animals, with their circadian rhythms tuned to a 24-hour cycle, would find their internal clocks running out of sync with the external environment. Only organisms that could radically adapt, or those living in buffered environments like deep caves or the deep ocean, might persist unchanged. The sky itself would look dramatically different. On the daylit side, the sun would dominate, rendering stars invisible during the 6-month-long day. On the dark side, the stars would be visible constantly, never interrupted by daylight. The moon, if it still orbited Earth, would go through all its phases over the course of a month as seen from the dark side, providing the only significant variation in illumination. The solar wind, normally distributed around Earth by its rotation, would blast the daylit side constantly, while the dark side remained in Earth's magnetotail, creating asymmetric auroral displays. The psychological impact of these conditions on any surviving humans would be profound. Humans evolved under a 24-hour day-night cycle, and our psychology and sociology are deeply influenced by this rhythm. The division of time into days, the structuring of work and rest, the social rhythms of daily life, all depend on the regular alternation of day and night. Without this cycle, human societies, if they survived at all, would need to completely reinvent how they organize time and activities. Imagine trying to sleep under the permanent glare of the sun, even if you were fortunate enough to be far enough from the subsolar point that the temperature was survivable. The light would be unrelenting, making true darkness impossible without shelter. Your circadian rhythm, evolved over millions of years to respond to light and dark, would be thrown into chaos. Sleep disorders would likely be universal. The concept of a day would become meaningless, perhaps replaced by arbitrary time divisions bearing no relationship to any celestial cycle. On the dark side, the opposite problem would arise. Permanent darkness would be equally disorienting, and humans would need artificial light sources constantly. The cold would be another challenge, requiring substantial energy for heating. Psychological disorders related to darkness and isolation would likely be common. Humans are creatures of light and warmth, and the permanent night of the dark hemisphere would challenge us in fundamental ways. As you relax deeper into sleep, imagine the Terminator slowly creeping across Earth's surface as our planet orbits the sun. That narrow band of twilight, moving slowly around the globe over the course of a year, might be the only place where the concept of seasons would remain. But instead of seasons of temperature and daylight hours, they would be seasons of sun position. The sun gradually rising, reaching its highest point at the horizon, then gradually setting again over 6 months, only to repeat the cycle. In that twilight realm, perhaps, something like life as we know it could persist, adapted to an eternal dawn or dusk, never experiencing the full glory of high noon or the complete peace of midnight. Deep beneath our feet, about 3,000 kilometers down, lies Earth's outer core, a seething ocean of molten iron and nickel at temperatures exceeding 5,000 degrees Celsius. This is not a still, quiet realm. The liquid, metal convects vigorously, driven by the heat flowing out from the even hotter inner core and the cooling effect of the overlying mantle. This convection would happen regardless of Earth's rotation, but rotation adds a crucial organizing principle to the chaos. Earth's spin, through the Coriolis effect, organizes these convection currents into columns and patterns that align with the rotation axis. These organized flows of electrically conductive liquid iron generate electric currents, and these electric currents generate magnetic fields. This is Earth's dynamo. The magnetic field produced by this dynamo is what we call the geomagnetic field, and it extends far out into space, creating the magnetosphere that shields our planet from the solar wind and cosmic radiation. Without this field, the sun's particles would strip away our atmosphere over geological time, and life on the surface would be exposed to harmful radiation that would make complex life impossible. Mars, which lost its magnetic field billions of years ago, shows us what happens. A thin atmosphere, a barren surface, no liquid water. Earth's magnetic field is thus not just a curious phenomenon. It's a critical component of our planet's habitability. The strength of Earth's magnetic field at the surface is about 25 to 65 microteslas, depending on where you measure. This is strong enough to deflect a compass needle, but weak compared to, say, a refrigerator magnet. Yet this seemingly weak field extends tens of thousands of kilometers into space, creating a protective bubble that deflects the charged particles streaming out from the sun. Without this deflection, those particles would interact directly with our atmosphere and surface, creating problems ranging from increased cancer rates to the erosion of our atmospheric gases. Now imagine Earth's rotation gradually slowing and eventually stopping. The convection in the outer core would continue. Heat would still flow, metal would still move, electric currents would still exist. But without rotation to organize these flows, the currents would become chaotic and turbulent rather than organized. The magnetic field they generate would become weaker and more complex, less like a simple bar magnet and more like a tangled mess of small magnetic fields pointing in different directions. The dynamo effect requires not just convection, but organized convection. Computer simulations of non-rotating planets show that their magnetic fields, if they exist at all, are much weaker and more chaotic than Earth's current field. The loss of the Coriolis effect removes the mechanism that creates the large-scale organization needed for a strong dipole field aligned with the rotation axis. Instead, you get small-scale, rapidly changing fields that don't add up to a strong global field. The timescale for this decline would depend on how quickly Earth's rotation slowed. If the slowdown happened over thousands of years, the magnetic field would gradually weaken over that same time period. If rotation stopped suddenly, impossible, but for argument's sake, the field would begin to decay immediately but wouldn't disappear instantly. The molten iron in the outer core has enormous momentum, both rotational and convective. It would take decades or even centuries for the rotation in the core to fully dissipate, and during that time, some level of magnetic field would persist. As the field weakened, the first noticeable effects would be on technology. Earth's magnetic field plays a crucial role in protecting satellites and electronic systems from solar storms and cosmic radiation. Many modern technologies, from GPS to power grids to communication satellites, depend on the magnetic shield to protect them from charged particles. As the field weakened, these systems would experience more frequent disruptions. Satellites would fail more often. Power grids would be more vulnerable to damage from solar flares. Navigation systems, dependent on Earth's magnetic field, would become unreliable. The compass, that ancient navigation tool, would become increasingly useless. A compass works by aligning with Earth's magnetic field, pointing toward the magnetic poles. As the field weakened and became more chaotic, compasses would point in random directions or spin aimlessly, no longer able to find a consistent magnetic north. For centuries, humanity navigated using compasses, trusting in the steady, reliable direction of Earth's magnetic field. That reliability would be lost, forcing us to rely entirely on other navigation methods. More seriously, the weakening magnetic field would begin to expose Earth's surface to higher levels of radiation. Cosmic rays, which are high-energy particles from supernovae and other violent cosmic events, are currently deflected by the magnetosphere. Some still reach the surface, especially near the poles where the field lines converge, but most are turned away. Without this protection, cosmic ray flux at the surface would increase significantly. For humans, this means higher cancer rates and increased genetic damage. For other organisms, particularly those without sophisticated DNA repair mechanisms, it could mean higher mutation rates and reproductive challenges. The solar wind, that constant stream of charged particles flowing out from the sun, would begin to interact directly with Earth's upper atmosphere. Currently, the magnetosphere deflects most of these particles around the planet. Those that do enter, typically at the poles, create the beautiful auroras as they interact with atmospheric gases. In a world with a weak or absent magnetic field, the solar wind would hit the atmosphere directly across the daylit hemisphere, potentially creating global auroral displays, but also stripping away atmospheric gases. This atmospheric erosion would be slow by human standards, but significant over geological time. Mars lost much of its atmosphere this way after its magnetic field disappeared about 4 billion years ago. Earth, starting with a much thicker atmosphere, would not face immediate atmospheric loss. But over millions of years, the solar wind would gradually erode the upper atmosphere, particularly lighter gases like hydrogen and helium. Water vapor would be broken apart by ultraviolet radiation, and the hydrogen would escape to space, gradually drying the planet. The Van Allen radiation belts, regions of trapped charged particles held in place by Earth's magnetic field, would disappear. These belts, discovered in the 1950s, extend from about 1,000 to 60,000 kilometers above Earth's surface. They contain high-energy protons and electrons trapped in the magnetic field. Without the field to trap them, these particles would either escape to space or fall into the atmosphere. For satellites and astronauts, this would actually be somewhat beneficial, as the Van Allen belts are a radiation hazard. But their disappearance would be another sign of the magnetic shield's collapse. Animals that navigate using Earth's magnetic field would be immediately affected. Many species, from sea turtles to birds to certain bacteria, have biological magnetoreception. They can sense Earth's magnetic field and use it for navigation during migration or for orienting themselves. Sea turtles, born on beaches, navigate across thousands of kilometers of ocean using the magnetic field as a map. Migratory birds use it as a compass on their seasonal journeys. With the field weakening and becoming chaotic, these species would lose their primary navigation tool, potentially leading to mass strandings and failed migrations. The atmosphere itself might undergo subtle changes. Earth's magnetic field influences the ionosphere, the upper layer of atmosphere where atoms are ionized by solar radiation. The ionosphere affects radio wave propagation, creating the layers that allow AM radio signals to bounce around the globe. It also plays a role in atmospheric chemistry and dynamics. Changes to the magnetic field would alter the ionosphere's structure and behavior, potentially affecting climate and weather in ways that are not fully understood. Solar storms, which currently create spectacular auroras and occasionally disrupt technology, would become more directly threatening. During a major solar storm, the sun ejects a massive cloud of charged particles that can reach Earth within a day or two. Currently, our magnetosphere compresses and fluctuates during these events, creating enhanced auroras and some technological disruptions. Without the magnetic shield, these storms would interact directly with the atmosphere, potentially creating more severe technological impacts and exposing the surface to dangerous radiation levels. In the very long term, the loss of the magnetic field would be a slow-motion catastrophe for complex life on Earth's surface. Increased radiation levels would make the surface increasingly hostile. Evolution would favor organisms with better radiation protection, perhaps those that could produce melanin-like compounds over their entire bodies, or those that could live primarily underground. The loss of atmospheric gases would eventually reduce air pressure and alter the composition of the atmosphere. Earth would begin a slow transformation towards something more like Mars, a cold, dry world with a thin atmosphere and a surface bathed in radiation. Let this knowledge settle over you like a blanket as you drift towards sleep. The magnetic field, invisible and intangible, is one of those background features of our world we rarely think about, but that is absolutely essential to life as we know it. It exists because Earth spins, because that spin organizes the chaos in our planet's molten core into patterns that generate protection. Rotation, that simple turning, creates not just day and night, not just weather and seasons, but the invisible shield that keeps our atmosphere intact and our surface safe from the worst of space's dangers. Rest easy, knowing that this shield is strong, stable, and will remain so as long as Earth keeps spinning. Weather, in all its complexity and variability, is fundamentally a product of Earth's rotation. The great circulation patterns that distribute heat from equator to poles, the jet streams that drive storm systems across continents, the monsoons that water vast agricultural regions, the hurricanes that form in tropical oceans, all of these depend critically on the Coriolis effect and the day-night cycle created by Earth's spin. On a non-rotating Earth, weather as we know it would cease to exist, replaced by something radically different and, in many ways, more extreme. The primary driver of weather is the uneven heating of Earth's surface. The equator receives more solar energy per unit area than the poles because the sun's rays strike the equator more directly. On our rotating Earth, this heat differential drives a complex system of atmospheric circulation cells. Air heated at the equator rises, flows toward the poles at high altitude, sinks in the mid-latitudes, and flows back toward the equator at the surface. These cells, combined with the Coriolis effect, create the trade winds, westerlies and polar easterlies that characterize our current climate system. On a non-rotating Earth, this circulation would be radically simplified. With no Coriolis effect to deflect moving air, the circulation would consist of just two giant convection cells, one in each hemisphere. Hot air from the subsolar point on the daylit side would rise straight up, flow across the sky toward the dark side, sink as it cooled over the cold, dark hemisphere, and then flow back toward the subsolar point along the surface. This simple two-cell circulation would create surface winds of extraordinary power, all flowing in the same direction, from the subsolar point toward the dark side at high altitude, and from the dark side back toward the subsolar point at the surface. These surface winds would make current hurricanes seem gentle by comparison. The temperature difference between the superheated subsolar point and the frozen dark side would be several hundred degrees Celsius. This extreme temperature gradient would drive winds at velocities potentially exceeding several hundred miles per hour. These would not be localized storms that come and go. They would be permanent, planet-encircling wind belts, flowing day after day, year after year, shaped only by the topography of mountains and the drag of the surface. The Terminator region, where the daylit and dark sides meet, would be a zone of incredible atmospheric violence. This is where the hot air flowing from the daylit side would meet the cold air flowing from the dark side. The collision would create a band of permanent storms encircling the globe, with violent updrafts and downdrafts, extreme precipitation, and winds that would constantly shift and swirl. Think of it as a planetary-scale version of a cold front, but one that never moves away, never resolves, just churns constantly at the boundary between two different worlds. Clouds would form in patterns completely unlike what we see today. On the daylit side, particularly around the subsolar point, the intense heating would create towering convective clouds that might reach to the edge of space. These clouds would form, produce brief but intense rainfall, evaporate, and reform in an endless cycle. The clouds would be purest white against the blue sky, constantly churning, constantly fed by the evaporation of what little water remained on the hot surface. On the dark side, clouds would form differently. Air flowing from the hot daylit side would carry moisture, which would condense and freeze as the air cooled over the dark hemisphere. This would create thick cloud layers covering much of the dark side, composed not of water droplets but of ice crystals. Snow would fall continuously in many regions of the dark side, accumulating into growing ice sheets. These cloud layers would trap some of the Earth's internal heat, preventing the dark side from cooling quite as much as it otherwise would, but they would also block any starlight, making the dark side even darker. Hurricanes, those magnificent and terrifying storms that form in tropical oceans, would cease to exist. Hurricanes depend critically on the Coriolis effect to create their characteristic rotation. Without the Coriolis effect, there would be no mechanism to start a low-pressure system spinning. The storms that formed would be more like giant thunderstorms than hurricanes, violent but not organized into the spiral structure we associate with tropical cyclones. The immense hurricanes that occasionally devastate coastal regions would be replaced by a different kind of meteorological threat: the unending blast furnace winds of the subsolar region and the permanent storm belt of the Terminator. Precipitation patterns would be utterly transformed. Currently, rain falls in patterns determined by atmospheric circulation, prevailing winds, and the day-night cycle. Some regions are wet, some dry, based on their position relative to these patterns. On a non-rotating Earth, precipitation would follow the simple rule: heavy rain and snow where air is rising and cooling, little or no precipitation where air is sinking and warming. The subsolar point would be dry despite the heat, as air there would be constantly rising, preventing rain formation. Rain would fall in a band around the edges of the daylit hemisphere as the air cooled and its moisture condensed. Snow would fall across much of the dark side as moisture brought from the daylit side froze out of the air. The concept of seasons, as we currently understand them, would effectively disappear. Seasons exist because Earth's rotation axis is tilted relative to its orbital plane, causing different parts of the planet to receive more or less direct sunlight as Earth orbits the Sun. This creates the familiar cycle of summer and winter. On a non-rotating Earth, while the tilt would still exist, its effect would be different. Over the course of a year, the subsolar point would migrate from the Tropic of Cancer to the Tropic of Capricorn and back, creating a slow shift in which hemisphere was slightly warmer. But this would be a subtle effect compared to the overwhelming dominance of the day-side versus night-side temperature difference. The jet streams, those fast-flowing rivers of air in the upper atmosphere that guide weather systems around the globe, would disappear. Jet streams form at the boundaries between air masses of different temperatures and are strongly influenced by the Coriolis effect. They typically flow from west to east and create the wavy patterns that bring warm and cold air masses into different regions. Without rotation, there would be no jet streams, just the simple flow from hot to cold described earlier. Weather would become more predictable in some ways, but also more extreme and less varied. Cloud streets, those parallel lines of clouds that form when wind flows over terrain or temperature boundaries, would form in strange new patterns. On the daylit side, they might radiate outward from the subsolar point like spokes on a wheel, marking the flow of air outward from the hottest point. On the dark side, they might converge toward the coldest point, marking the flow of air toward the heat sink of the frozen night. From space, Earth would look utterly alien, its cloud patterns geometric and organized by the simple radial flow rather than the complex, chaotic patterns created by rotation. The water cycle, that endless circulation of water from ocean to atmosphere to land and back, would be disrupted in fundamental ways. Currently, water evaporates from oceans and land, is transported by winds, falls as precipitation, flows through rivers back to the ocean, and the cycle continues. On a non-rotating Earth, water would evaporate primarily from the hot daylit side and from the polar oceans in the scenario where Earth has stopped rotating and oceans have migrated to the poles. This moisture would be transported to the cold dark side, where it would fall as snow and accumulate as ice. Over time, water would gradually be transferred from the daylit side to the dark side, locked up in massive ice sheets, creating a runaway imbalance. The atmospheric pressure would be dramatically different from today. The heating of the daylit side would cause the air there to expand and rise, creating lower pressure at the surface. The cooling of the dark side would cause the air to contract and sink, creating higher pressure. This pressure gradient would be much larger than any pressure differences we currently experience, and it would be permanent rather than transient. The winds flowing from high to low pressure would be correspondingly stronger. Temperature records would become meaningless. Currently, we track daily high and low temperatures, note heat waves and cold snaps, and measure climate change by shifts in these averages. On a non-rotating Earth, temperatures would not fluctuate daily. Instead, they would vary based on position. Hottest at the subsolar point, coldest at the antisolar point, moderate at the terminator. Temperature records would become maps rather than time series, showing spatial variation rather than temporal variation. The concept of a heat wave would be replaced by the concept of too close to the subsolar point. The idea of a cold snap would be replaced by too far into the dark side. As you continue to relax, imagine the wind, no longer coming from the familiar directions of north, south, east, or west, but always from the same direction relative to the sun. On the daylit side, wind always blowing outward from the subsolar point. On the dark side, wind always converging toward the coldest region. The terminator, a zone of eternal storm, neither day nor night, but something in between, where wind direction shifts chaotically as competing air masses battle for dominance. Weather reduced to its fundamental essence, heat flowing from hot to cold, air rising and falling, water evaporating and condensing, all in patterns determined by the simple geometry of a sun that never moves and a planet that never turns. Let that steady, unchanging flow lull you toward deeper rest. Life on Earth has been shaped by the planet's rotation since the first self-replicating molecules emerged in ancient oceans billions of years ago. The 24-hour cycle of day and night has been such a constant feature of our world that it is literally encoded in the DNA of every living thing. From the simplest bacteria to the most complex animals, organisms have evolved internal biological clocks that run on approximately 24-hour cycles. These circadian rhythms are not learned behaviors. They are fundamental biological mechanisms maintained by networks of genes and proteins that create oscillating chemical signals within cells. In humans, the circadian rhythm regulates when we feel sleepy and when we feel alert, when our body temperature rises and falls, when certain hormones are released into our bloodstream, and when our cells are most actively repairing DNA damage. The suprachiasmatic nucleus, a tiny cluster of about 20,000 nerve cells in the hypothalamus, acts as the master clock, receiving light signals from the eyes and using that information to synchronize all the peripheral clocks throughout the body. This system, honed by millions of years of evolution, assumes a reliable 24-hour light-dark cycle. On a non-rotating Earth, this system would be completely disrupted. For organisms on the daylit side, exposed to constant light, their circadian rhythms would initially continue to cycle with their natural period of slightly more than 24 hours. But without the daily reset provided by darkness, these rhythms would gradually drift out of sync with each other and with the environment. Sleep would become increasingly difficult. Hormone cycles would become erratic. Metabolic processes that depend on circadian timing would fail. Over time, organisms might evolve to eliminate their circadian rhythms entirely, or they might develop new timing systems based on other environmental cues, but the transition period would be brutal. Animals on the dark side would face opposite but equally severe challenges. Their circadian rhythms, evolved to respond to light, would find no light signals to reset them. In experiments, animals kept in constant darkness show free-running rhythms that gradually drift, just like those in constant light. But humans and other animals do not thrive in constant darkness. Depression, lethargy, and metabolic problems are common. The psychological burden of unending night, combined with the extreme cold, would make the dark side of a stopped Earth essentially uninhabitable for complex animals. Plants would face perhaps the most severe challenges. Photosynthesis, the process by which plants convert sunlight into chemical energy, is essential not just for plants, but for virtually all life on Earth. Plants have evolved sophisticated mechanisms to maximize photosynthesis during daylight while protecting themselves from excessive light and heat. On the permanent daylit side, plants would need to evolve ways to cope with relentless radiation and heat. Many would likely die, their leaves scorched, their roots unable to find adequate water in the baked soil. Only the most heat-tolerant, drought-resistant species would have any chance of survival. On the dark side, photosynthesis would become impossible without sunlight. Plants could not grow, could not produce the oxygen that animals breathe, could not form the base of the food chain. Any plants that somehow survived the transition to eternal night would be living off stored energy, gradually depleting their reserves until they died. The only possibility for plant life would be in the twilight zone along the terminator, where dim light from the perpetually low sun might allow some minimal photosynthesis. Ecosystems, those complex webs of interacting species that have developed over millions of years, would collapse completely. An ecosystem depends on energy flow from the sun, through plants, to herbivores to carnivores, with decomposers breaking down dead material and returning nutrients to the soil. Without the regular day-night cycle, this flow would be disrupted at every level. The timing of flowering, the schedules of pollination, the seasonal migrations, the hibernation cycles, all would be thrown into chaos. Species that depend on each other would find themselves out of sync, unable to fulfill their ecological roles. Consider a simple example. Bees and flowers. Many flowering plants bloom during specific times of day when their pollinators are most active. Bees have circadian rhythms that make them most active during daylight hours when flowers are open and nectar is available. On a non-rotating Earth, this synchronized timing would break down. Flowers on the daylit side might close to protect themselves from the constant heat, becoming unavailable to pollinators. Or bees might stop following any consistent activity pattern, becoming active at random times. The partnership between plants and pollinators, refined over millions of years of coevolution, would dissolve. The ocean ecosystems would fare somewhat better than terrestrial ones, as the deep ocean is already a world of eternal darkness where life has adapted to function without direct sunlight. But even ocean life would struggle. Many marine organisms migrate vertically in the water column on a daily basis, rising toward the surface at night to feed and descending during the day to avoid predators. This behavior, driven by circadian rhythms and cued by light levels, would become impossible on a non-rotating Earth. The surface waters on the daylit side would become superheated, killing most life there. Only the deep ocean, buffered from the extreme conditions at the surface, might maintain something resembling normal marine ecosystems. Microorganisms, particularly bacteria and archaea, would likely be the most resilient to the loss of rotation. Many microbes already live in extreme environments with no day-night cycle, such as deep underground or in hot springs. These organisms have metabolisms that don't depend on photosynthesis or circadian rhythms. Some bacteria can enter dormant spore states that allow them to survive almost any condition. In the long term, if complex life died out, the microbial world might persist and even thrive, slowly recolonizing the surface as conditions changed over geological time. But what of humans specifically? Humans have the advantage of technology. We could, theoretically, create artificial environments with controlled lighting that mimicked a day-night cycle. Deep underground bunkers or enclosed habitats along the terminator might provide refuge. We could grow food using artificial light, recycle water and air, and shield ourselves from the radiation and temperature extremes. But such an existence would be a far cry from the world we know. The population that could be sustained would be a tiny fraction of current levels. Most of humanity would perish in the initial catastrophe or its aftermath. Those who survived would live in isolated pockets, probably never to rebuild global civilization as we know it. The psychological effects on survivors would be profound. Humans are diurnal creatures who have lived under a 24-hour day for our entire evolutionary history. Our sense of time, our social structures, Our very sense of self is built around this rhythm. Living in an artificial environment with no connection to natural light and darkness, or living in the perpetual twilight of the Terminator, would require radical psychological adaptations. Depression, anxiety, and cognitive problems would likely be common. The concept of a day would become an artificial construct, maintained by clocks rather than celestial motion. Children born in such a world would grow up never knowing natural sunrises or sunsets, never experiencing the gentle progression from day to night. The cultural importance of these transitions, embedded in our language, literature, and traditions, would gradually fade into mythology. Future generations might look back on the time when Earth rotated and people experienced daily cycles of light and dark as a kind of paradise lost, a time when the world made sense in ways it no longer could. Yet life has proven remarkably resilient throughout Earth's history. Mass extinctions have occurred, wiping out large percentages of species, yet life has always recovered, evolving new forms to fill empty ecological niches. If Earth's rotation stopped gradually enough, over thousands or millions of years rather than suddenly, life would have time to adapt. Evolution works quickly when selection pressure is strong. Species that by chance had traits allowing them to tolerate longer days and nights would survive and reproduce. Over many generations, new organisms would emerge adapted to the new conditions. Life would persist, though in forms very different from what we see today. As you continue to relax, breathing slowly and deeply, imagine a world transformed but not destroyed. Life clinging to the edges, adapting, persisting in the face of unimaginable change. The Terminator Zone, that band of eternal twilight, becoming a refuge for the hardy species that could tolerate its strange conditions. Deep ocean trenches harboring communities of organisms unchanged by surface catastrophes. Underground ecosystems thriving in eternal darkness, sustained by Earth's internal heat rather than the sun. Life, that persistent creative force, finding ways to continue even when the fundamental rhythms of the planet have been altered beyond recognition. Sleep now, knowing that life is more resilient than we imagine, and that the steady spin that has supported us for so long continues uninterrupted, as it has for billions of years and will for billions more. Let us step back from catastrophe and contemplate the elegant physics that keeps Earth spinning. Understanding why Earth spins and what maintains that spin reveals fundamental truths about the universe, from the conservation laws that govern all motion to the subtle interactions between celestial bodies that shape the evolution of planetary systems over billions of years. Earth's rotation is not something that was started and needs continued energy input to maintain. Rather, it's a consequence of angular momentum, a fundamental property of rotating objects that is conserved in the absence of external torques. Angular momentum, in simple terms, is the rotational equivalent of linear momentum. Just as a moving object tends to keep moving in a straight line unless acted upon by a force, a rotating object tends to keep rotating unless acted upon by a torque. When our solar system formed from a collapsing cloud of gas and dust approximately 4.6 billion years ago, that cloud had some net angular momentum. Perhaps the cloud was given a gentle nudge by a nearby supernova explosion, or perhaps it inherited rotation from the larger galactic structures from which it condensed. Regardless of the source, once the cloud had any rotation at all, that rotation was preserved as the cloud collapsed. As the cloud contracted under its own gravity, conservation of angular momentum dictated that it must spin faster, just as a figure skater spins faster when pulling their arms inward. This accelerating rotation caused the collapsing cloud to flatten into a disk with most of the mass falling to the center to form the sun and the remaining material spreading out in a thin disk around it. Within this disk, small particles collided and stuck together, gradually building up larger and larger objects through a process called accretion. These growing planetesimals inherited the rotation of the disk material from which they formed. By the time Earth had accreted to its final size, it possessed substantial angular momentum, causing it to spin on its axis. The exact spin rate and axis orientation of the young Earth were determined by the details of the final stages of accretion. Computer simulations suggest that the young Earth was struck by a Mars-sized object in a glancing blow, an impact so violent it ejected enough material to form the Moon. This giant impact would have transferred angular momentum to Earth, possibly speeding up its rotation dramatically. In the immediate aftermath of this collision, Earth may have been spinning much faster than today, with a day lasting only a few hours. But why does Earth continue to spin billions of years later? The answer lies in that same principle of conservation of angular momentum. In the absence of external torques, angular momentum is preserved. Earth's rotation would continue forever at a constant rate if it were truly isolated in space. But of course, Earth is not isolated. It exists in a system with the Moon, the Sun, and other planets, all of which exert gravitational forces. These forces create torques that gradually alter Earth's rotation over time. The most significant torque acting on Earth comes from tidal interactions with the Moon. The Moon's gravity creates bulges in Earth's oceans and, to a lesser extent, in Earth's solid body. Because Earth rotates faster than the Moon orbits, these tidal bulges are carried ahead of the Earth-Moon line by Earth's rotation. The Moon's gravity pulling on these leading bulges creates a torque that acts to slow Earth's rotation. This tidal braking has been gradually lengthening Earth's day throughout its history, a process that continues today at a rate of about 1.4 milliseconds per century. The angular momentum lost by Earth's rotation doesn't disappear. It is transferred to the Moon's orbit through the gravitational interaction between the Moon and the tidal bulges. As Earth loses rotational angular momentum, the Moon gains orbital angular momentum, causing it to spiral slowly away from Earth. Currently, the Moon is receding at a rate of about 3.8 centimeters per year, as measured by laser-ranging experiments that bounce laser beams off reflectors left on the lunar surface by Apollo astronauts. This process will continue far into the future. Billions of years from now, if the Sun doesn't end life on Earth first by expanding into a red giant, Earth and Moon will reach a state called double synchronous rotation. In this configuration, Earth's rotation period will equal the Moon's orbital period. Earth will rotate once for each orbit of the Moon, meaning the same side of Earth will always face the Moon, just as the same side of the Moon always faces Earth today. At that point, the tidal bulges will be perfectly aligned with the Earth-Moon line, no longer creating any net torque, and the Earth-Moon system will be in a stable configuration with no further transfer of angular momentum. The rate at which Earth's rotation slows is not perfectly constant. Small variations occur due to many factors, including the redistribution of mass within Earth. When glaciers melt and water flows to the oceans, mass moves from near the poles toward the equator, increasing Earth's moment of inertia. To conserve angular momentum, Earth's rotation must slow down slightly when this happens. Similarly, major earthquakes that shift large amounts of crust can minutely alter Earth's moment of inertia and thus its rotation rate. Even changes in atmospheric winds and ocean currents, which have their own angular momentum, can affect Earth's rotation on timescales of weeks to years. Scientists monitor Earth's rotation with extraordinary precision using techniques such as very long baseline interferometry, which observes distant quasars using radio telescopes spread across the globe. By comparing the arrival times of radio signals from these quasars at different telescopes, astronomers can determine Earth's orientation in space to within a few millimeters. These measurements reveal all sorts of small variations in Earth's rotation, from the tidal effects of the moon and sun to the effects of seasonal winds and even the redistribution of groundwater after heavy rains. One interesting consequence of these measurements is that Earth's rotation doesn't keep perfect time with atomic clocks. Atomic clocks, which count the oscillations of atoms, keep extremely precise time based on fundamental physics. But Earth's rotation, affected by all the factors mentioned above, varies slightly in unpredictable ways. To keep our civil time synchronized with Earth's rotation, scientists occasionally add or subtract leap seconds from our clocks. Since leap seconds were introduced in 1972, we've added 27 of them, reflecting the gradual slowdown in Earth's rotation. The physics of Earth's rotation connects to broader questions about the evolution of planetary systems. All the planets in our solar system rotate, though at vastly different rates and with different axial tilts. Mercury rotates very slowly, taking 58.6 days for one rotation. Venus rotates even more slowly and in the opposite direction from most planets, taking 243 days for one rotation. The gas giants rotate very rapidly. Jupiter completes a rotation in just under 10 hours, despite being the largest planet. These differences reflect the varied histories of these worlds, the impacts they've suffered, the tidal interactions they've experienced. Earth's axial tilt of 23.5 degrees is particularly important for life. This tilt gives us seasons, as different parts of Earth receive more or less direct sunlight as we orbit the Sun. The tilt is thought to have been established by the giant impact that formed the Moon. Without this tilt, Earth would have no seasons. The equator would always be hot, the poles always cold, with no seasonal variation to drive atmospheric circulation or ocean currents in the ways we're familiar with. The stability of Earth's axial tilt over geological time is partly due to the Moon. Computer simulations of Earth without the Moon show that the axial tilt would vary chaotically over time, swinging from nearly upright to nearly on its side as perturbations from other planets accumulated. These variations would create wild swings in climate as the distribution of sunlight changed. Mars, which has a much smaller satellite system, shows evidence of exactly this kind of chaotic axial tilt variation, which may explain its complex climate history. The rotation of Earth also generates the magnetic field that protects our atmosphere from erosion by the solar wind. Deep in Earth's core, the outer layer of molten iron and nickel convects vigorously, driven by heat from the inner core and cooling from the mantle above. Earth's rotation, through the Coriolis effect, organizes these convection currents into columns aligned with the rotation axis. These organized flows of electrically conductive liquid iron act as a dynamo, generating electric currents, which in turn generate the magnetic field. This is called the geodynamo, and it's been operating for at least 3.5 billion years based on evidence from ancient rocks that preserve the direction of Earth's magnetic field when they solidified. If Earth stopped rotating, the geodynamo would gradually shut down. The convection would continue, but without the organizing influence of rotation, the magnetic field would become weaker and more chaotic. Eventually, it might disappear entirely, leaving Earth's atmosphere vulnerable to erosion by the solar wind, much like what happened to Mars after its magnetic field died billions of years ago. The mathematics of rotation are elegant and reveal deep truths about the symmetry of space. Angular momentum is a vector quantity, meaning it has both magnitude and direction. The direction of Earth's angular momentum vector points along its rotation axis northward by convention. The magnitude depends on Earth's mass distribution and rotation rate. For a sphere, angular momentum equals 2/5 times the mass times the square of the radius times the angular velocity. For Earth, this works out to about 5.8 times 10 to the 33rd kilogram meters squared per second, an almost incomprehensibly large number. This enormous angular momentum makes Earth's rotation incredibly stable. To change it significantly would require forces beyond anything available in nature, short of catastrophic collisions with other planetary bodies. Even the most powerful earthquakes, which release energy equivalent to thousands of nuclear weapons, barely affect Earth's rotation, changing the length of day by a few microseconds at most. As you settle deeper into relaxation, let these thoughts of cosmic clockwork soothe your mind. Earth spins because it was born spinning, inheriting rotation from the vast cloud that collapsed to form our solar system. It continues spinning because that rotation is preserved by the fundamental laws of physics, laws that govern everything from the smallest subatomic particles to the largest galaxy clusters. The same principles that keep Earth rotating keep electrons orbiting atomic nuclei and galaxies spinning in space. We live in a universe built on conservation laws and symmetries, a universe where motion once started tends to persist, where patterns echo from the quantum scale to the cosmic. Sleep now in a universe that makes sense, governed by comprehensible rules, where Earth's steady spin is just one example of the eternal dance of rotating bodies that fills the cosmos. Earth's rotation is our fundamental timekeeper, the clock by which all other clocks are ultimately calibrated. The division of time into days, hours, minutes, and seconds is not arbitrary, but rooted in the simple fact that Earth turns on its axis once every 24 hours. If Earth stopped rotating, we would need to completely reimagine how we measure and experience time. Currently, one day is defined as the time it takes Earth to rotate once relative to the Sun. This is called a solar day, and it's the basis for our civil timekeeping. We divide this day into 24 hours, each hour into 60 minutes, and each minute into 60 seconds. These divisions are ancient, inherited from Babylonian astronomers who used a base 60 number system. But the fundamental unit, the day, comes directly from Earth's rotation. On a non-rotating Earth, the concept of a day in the traditional sense would cease to exist. The sun would not rise and set daily. There would be no obvious cycle to use as a basis for timekeeping. Humans would need to adopt some arbitrary period as our basic time unit. Perhaps we would use Earth's orbital period, defining a year as our basic unit and dividing it into smaller increments. Or perhaps we would simply use the duration of a previous Earth day, maintaining the 24-hour cycle as a convenient standard even though it no longer corresponded to any celestial motion. But this would create a profound disconnect between our clocks and our experience. Currently, time and the cycles of nature are intimately linked. We wake with the sun, work during the day, sleep at night. The passage of time is marked by visible changes in our environment. Dawn giving way to morning, afternoon fading into evening, night deepening toward midnight. On a non-rotating Earth, this connection would be severed. Time would become purely abstract, measured by clocks but not reflected in any changing sky or shifting light. Our biological clocks, evolved to track the 24-hour day, would be thrown into confusion. The suprachiasmatic nucleus in our brains, that tiny cluster of neurons that serves as our master circadian pacemaker, receives input from light-sensitive cells in our eyes. These cells detect the overall brightness level and use that information to synchronize our internal rhythms with the external day-night cycle. On the permanent daylit side of a stopped Earth, these cells would receive constant bright light signals, telling the brain it's always day. On the permanent dark side, they would receive no light signals, suggesting permanent night. Research on humans living in constant conditions provides some insight into what might happen. In one famous experiment, French scientist Michel Seffre spent 2 months living in a cave with no time cues, no clocks, no sunlight. He found that his natural sleep-wake cycle was slightly longer than 24 hours, about 24.5 hours. Without external cues to reset his internal clock daily, his rhythm gradually drifted later and later relative to the actual time outside the cave. Other studies have confirmed that the human circadian rhythm, when allowed to free run without time cues, typically has a period of about 24.1 to 24.3 hours. This slight difference between our internal clock and Earth's rotation is actually important. It means that our clocks need to be reset daily by external cues, primarily morning light, to stay synchronized with Earth's rotation. This daily resetting allows our biology to adapt to seasonal changes in day length and to recover from occasional disruptions in our schedule. But in an environment without any day-night cycle, this resetting mechanism would have nothing to work with, and people's rhythms would gradually drift, each person ending up on their own personal schedule determined by their internal clock period. The social consequences would be severe. Much of human social organization depends on shared time. We coordinate our activities by agreeing to meet at specific times, work during specific hours, conduct business during shared schedules. If everyone's biological clock was drifting at its own rate, this coordination would become impossible without strict adherence to artificial schedules maintained by clocks. People would need to fight their biology constantly, forcing themselves to wake and sleep according to socially determined schedules rather than their natural inclinations. The measurement of time itself would become more arbitrary. Currently, we can calibrate our clocks by observing celestial motions. Ancient sundials measured time by the sun's apparent motion across the sky. Later, mechanical clocks were calibrated to match the average length of the solar day. Atomic clocks, which now provide our most precise time standard, are ultimately calibrated so that a day contains exactly 86,400 seconds on average, maintaining continuity with the astronomical definition of time. On a non-rotating Earth, we would need new standards. Perhaps we would define the second based purely on atomic vibrations with no reference to Earth's motion at all. The second is already defined in terms of the oscillations of cesium atoms. Specifically, 1 second is defined as 9,192,631,770 periods of the radiation corresponding to the transition between two energy levels of cesium-133. This definition makes no reference to Earth's rotation and could serve as the basis for timekeeping in a stopped world. But even with atomic clocks providing precise time intervals, humans would need some longer cycle to organize their lives around. Shift work studies show that humans function best with regular schedules that include both activity and rest. We can't work continuously, we need sleep. We can't stay awake indefinitely, even with bright lights and stimulants. Some cycle would need to be maintained, even if arbitrary. Most likely, we would continue using a 24-hour cycle simply because it's close to our natural circadian period and we have millennia of cultural habits built around it. The concept of years would remain meaningful, as Earth would still orbit the Sun. A year would still mark the completion of one full orbit, the return of Earth to the same position in its orbit. Seasons would still exist in a sense, though they would be very different from what we know. As Earth orbited the Sun, the subsolar point would migrate from tropic to tropic over the course of the year. Regions that experienced the subsolar point directly overhead would face extreme heat for part of the year, while at other times, the Sun would hang lower in the sky, providing some relief. Historical records would become confusing. Currently, historical dates are referenced to Earth's rotation. When we say an event happened on a specific date at a specific time, we're implicitly referencing Earth's rotation. An event at noon happened when the Sun was at its highest point for that location. An event at midnight happened when the Sun was at its lowest point, on the opposite side of Earth. In a stopped world, these references would lose meaning. Future historians studying the time before Earth stopped would need to understand that time was measured differently then, that a day meant something specific that no longer applied. The psychological experience of time would change profoundly. Time perception in humans is influenced by many factors, but one important one is the regular alternation of day and night. This creates natural chapters in our lives, with each day being a self-contained unit with a beginning, middle, and end. On a non-rotating Earth, this natural chapter structure would disappear. Time might feel more continuous and undifferentiated, with no obvious landmarks to mark its passage except the arbitrary ones we impose with clocks and calendars. Seasonal affective disorder, that form of depression linked to reduced sunlight during winter, would become universal for people living on the dark side of Earth. The lack of sunlight would affect not just mood, but also vitamin D production, immune function, and overall health. Light therapy, which is sometimes used to treat seasonal affective disorder, would need to be continuous rather than seasonal. Essentially, everyone would need to live under artificial lights bright enough to provide the health benefits of sunlight. The loss of celestial navigation would be another subtle but significant change. For thousands of years, humans used the apparent motion of the sun, moon, and stars to navigate across land and sea. Sundials told time. The North Star showed direction, the positions of stars indicated latitude. On a non-rotating Earth, the stars would remain fixed in the sky rather than appearing to circle the celestial pole. The sun would not move across the sky but would hang in one position. Navigation would need to rely entirely on maps, compasses, and eventually electronic systems like GPS. The intimate connection between the sky and human wayfinding, developed over countless generations, would be severed. Children growing up in a stopped world would have no intuitive understanding of the concepts that come naturally to us. The words sunrise and sunset would be historical terms with no referent in lived experience. The idea of a day having a beginning and end would seem strange. Time would be purely abstract, something measured by devices rather than something that could be directly experienced through changes in the world. This might lead to a more precise but less poetic relationship with time, less connected to nature and more to human-constructed systems. Let these thoughts about time drift through your mind as you relax deeper. Time, which seems so absolute and unchanging, is actually deeply tied to the motion of our world. The ticking of clocks, the progression of days and nights, the rhythm of seasons, all flow from Earth's spinning and orbiting. We measure our lives in these units, celebrate birthdays marking full orbits of the sun, organize our days around the rising and setting of that same sun. Time and motion are inseparable, woven together in the very fabric of how we experience existence. Rest easy, knowing that Earth's reliable rotation provides us with a natural timekeeper, a clock written in the motions of the heavens, steady and true, measuring out our days and nights with metronomic precision. Sleep now and let time drift away. We have explored the catastrophic sudden stop and various aspects of a completely stopped Earth. Now let us consider a more realistic and, in some ways, more fascinating scenario. Earth's rotation gradually slowing over thousands or millions of years until it comes to a complete stop. This is actually happening right now, though on a timescale so slow that it poses no threat to civilization. But if the process were to accelerate somehow, or if we simply fast forward millions of years into the future, what would the transition look like? Currently, Earth's rotation is slowing at a rate of about 1.4 milliseconds per century due to tidal interactions with the Moon. At this rate, it would take roughly 640 million years for a day to lengthen by just 1 hour. The Sun will expand into a red giant and engulf Earth long before tidal braking brings Earth to a complete stop through natural processes. But let's imagine a scenario where the slowdown accelerates dramatically, perhaps due to some unknown phenomenon, and Earth transitions from its current rotation rate to zero rotation over, say, 1,000 years. In the first decades of this accelerated slowdown, the changes would be subtle but measurable. Days would begin lasting a few seconds longer than 24 hours, then a minute longer, then several minutes. At first, this might seem trivial. We already add leap seconds occasionally to account for irregular variations in Earth's rotation. A few extra seconds per day wouldn't fundamentally change daily life. People would adjust their schedules slightly, sleep a bit longer, and generally adapt. But as days grew to 25 hours, then 26, then 30, the effects would become more pronounced. The longer periods of daylight and darkness would begin to affect temperature patterns. Daytime temperatures in sunny regions would rise higher as the sun beat down for longer periods before night brought cooling. Nighttime temperatures would drop lower during the extended darkness. The daily temperature swing, currently moderated by the relatively quick alternation of day and night, would become more extreme. Plants and animals, with their finely tuned circadian rhythms, would begin to struggle. A 24-hour circadian clock is reasonably flexible. Many organisms can adapt to day lengths ranging from roughly 20 to 28 hours, though they show increasing signs of stress at the extremes. But as days lengthened beyond 30 hours, more and more species would find themselves unable to synchronize their internal clocks with the external cycle. Some plants might flower at the wrong times, missing their pollinators. Some animals might attempt to migrate based on internal cues that no longer match the actual seasons. Agriculture would face growing challenges. Crop plants, bred for thousands of years under 24-hour days, would show reduced yields under altered light cycles. Some crops might fail entirely. Farmers would need to develop new varieties adapted to longer days, a process that could take years or decades of selective breeding or genetic engineering. In the meantime, food production would decline, potentially leading to shortages and social unrest. The oceans would gradually begin their migration toward the poles as the equatorial bulge slowly flattened. This would be a gradual process, with sea levels dropping a few centimeters per year in equatorial regions and rising by similar amounts in polar regions. Coastal cities would need to adapt to changing waterlines. Over decades, ports that once sat on the coast would find themselves progressively farther inland. New coastlines would emerge as continental shelves were exposed. Nations would need to redraw maps and maritime boundaries as the geography of the seas changed. Weather patterns would shift as the Coriolis effect weakened. With slower rotation, the deflection of moving air masses would be less pronounced. Hurricane formation would become less frequent as hurricanes need a strong Coriolis effect to develop their characteristic rotating structure. Jet streams would slow and shift position. The great circulating cells of the atmosphere would begin to reorganize into simpler patterns. Climate zones would migrate, with some regions becoming wetter and others drier, some warmer and others cooler, as the global distribution of heat changed. By the time days reached 100 hours, over 4 current days per sunrise to sunrise cycle, civilization would be facing a true crisis. The agricultural system would be in chaos, ecosystems would be collapsing, mass migration would be underway as people fled regions becoming uninhabitable. But humans, being adaptable and technological, might still cope. We could build enclosed habitats with artificial lighting, grow food hydroponically, and use renewable energy from the still functioning solar and wind resources to power our civilization. As days lengthened to 1,000 hours, then 10,000 hours, Earth would be transitioning from a rotating world to a tidally locked one. The same hemisphere would face the sun for months at a time, baking under relentless heat before rotating to face away for another equally long period of darkness and cold. This transitional phase might actually be worse than a fully stopped Earth. At least in a tidally locked world, each region would have consistent conditions, always hot, always cold, or always twilight. But in this transitional phase, every region would experience wild temperature swings as it slowly rotated through extended periods of sun and darkness. The final stages, as Earth's rotation slowed from 1 rotation per year to 1 rotation per decade to effectively 0, would see the planet settling into its final configuration. The Terminator would slow its creep across the surface until finally coming to rest. The polar oceans would reach their final extent. The permanent day side and permanent night side would establish their steady-state climates. Life, if any remained outside of human-maintained habitats, would be concentrated in those lucky regions where conditions were tolerable, probably a narrow band around the Terminator. Interestingly, this gradual scenario gives life a chance to evolve and adapt. Evolution works on timescales of thousands to millions of years, and with a slowdown occurring over similar timescales, natural selection would favor organisms better adapted to the changing conditions. We might see the emergence of new species specially adapted to extremely long days and nights. Plants might evolve that could store enough energy during the long day to survive the long night. Animals might develop extreme forms of hibernation or estivation, becoming active only during the tolerable twilight periods between the extreme heat of day and extreme cold of night. Microorganisms would almost certainly adapt successfully. Bacteria and archaea have extremely short generation times and large populations, allowing rapid evolution. Within a few thousand generations, perhaps just a few years for fast reproducing bacteria, strains adapted to the new conditions would emerge. These might then evolve into more complex forms over millions of years, potentially giving rise to entirely new ecosystems adapted to a non-rotating world. Human civilization, if it survived the transition, would be transformed beyond recognition. We would become a primarily underground or enclosed species, living in controlled environments with artificial day-night cycles. Our connection to the natural world would be severed. Future generations might know Earth's surface only from historical records and scientific expeditions, living their entire lives in climate-controlled habitats. The night sky would be visible only to those living on the dark side, while the day-side residents would see only the harsh glare of the sun. Some philosophers and scientists have speculated that technological civilizations might eventually choose to modify their planets deliberately. If humans survived long enough to develop truly advanced technology, we might decide to stop Earth's rotation intentionally, perhaps to facilitate some large-scale engineering project or to make the planet more easily inhabitable through the construction of controlled habitats. In such a scenario, the slowdown would be managed carefully to minimize damage and allow time for adaptation. Alternatively, future humans might choose to accelerate Earth's rotation, counteracting the natural tidal slowdown and maintaining a 24-hour day indefinitely. This would require enormous energy inputs, possibly from some advanced power source we haven't yet discovered. But it's not impossible in principle. If we can imagine stopping Earth, we can equally well imagine speeding it up or maintaining it at a constant rate. The gradual slowdown scenario highlights an important truth. Catastrophic change and gradual change are fundamentally different. A sudden stop would be absolutely fatal to virtually all complex life. But a very gradual slowdown, occurring over millions of years, would be something life could potentially adapt to. The difference is the time available for adaptation, for evolution to work its magic, for new solutions to emerge to new problems. As you drift towards sleep, consider this more hopeful scenario. Even in the face of tremendous change, life persists. Even as the fundamental parameters of our world shift, organisms find ways to adapt, to survive, to thrive in new conditions. The resilience of life, honed by billions of years of evolution, is extraordinary. From bacteria living in boiling acidic springs, to fish in the pitch-dark depths of the ocean, To organisms dormant in ice for thousands of years, life has proven capable of surviving in almost any condition Earth can provide. The slow changing of Earth's rotation, dramatic as it would just be another challenge for life to overcome. Rest now in the knowledge that life is tough, adaptable, and persistent, and that the changes we fear often bring new possibilities, new forms, new ways of being we cannot yet imagine. We have journeyed through 100 sleepy facts about a world without rotation, exploring catastrophic scenarios and gradual transitions, examining the physics and biology, the grand scale, and the intimate details. Now, as we draw this thought experiment to a close, let us reflect on what we have learned about our spinning home. Earth's rotation, something we never feel and rarely think about, is woven into every aspect of our existence. It shapes the length of our days and the rhythm of our lives. It drives our weather and ocean currents. It generates our protective magnetic field. It creates the Coriolis effect that influences everything from hurricanes to long-range artillery trajectories. It gives us regular transitions between light and dark that organize the activity of virtually every organism on the planet. Without rotation, Earth would not be the verdant, life-supporting world we know, but rather a harsh, alien landscape of extremes. Yet, this rotation is not unchanging. It is gradually slowing, a process that has been ongoing since Earth's formation and will continue for billions of years. The Moon, our constant companion, is slowly robbing us of rotational momentum, trading it for orbital distance. This is not a threat to life in any practical sense. The changes occur far too slowly for any species to notice within its evolutionary lifetime. But it reminds us that nothing in the universe is truly static. Everything changes, everything evolves, everything is in motion. The thought experiments we have explored reveal the delicate balance that makes our planet habitable. Earth is neither too large nor too small, neither too close to the sun nor too far, neither rotating too quickly nor too slowly. Its atmosphere is thick enough to trap heat and support life, but not so thick as to create a runaway. Greenhouse effect. Its magnetic field is strong enough to protect us, but not so strong as to interfere with the complex chemistry of life. Its tilt gives us seasons that are pronounced enough to drive atmospheric circulation, but not so extreme as to create uninhabitable polar regions for half the year. This balance is not unique to Earth, not in the cosmic sense. Billions of planets exist in our galaxy alone, and many of them undoubtedly have conditions that could support life. But each habitable world represents a delicate compromise between competing factors, a narrow region of parameter space where conditions allow complexity to emerge and persist. Earth's rotation is just one of many parameters that must fall within a certain range for life as we know it to exist. Understanding these connections between planetary motion and habitability helps us in the search for life elsewhere in the universe. When astronomers discover exoplanets orbiting other stars, one of the key questions they ask is whether the planet might be tidally locked to its star. Many exoplanets orbit very close to their stars, close enough that tidal forces would have locked their rotation to their orbital period over time. These planets would have permanent day sides and permanent night sides, just like the non-rotating Earth we have imagined. Are such worlds habitable? Could life adapt to the extreme conditions? The answer is still uncertain, but our thought experiments about a non-rotating Earth inform these questions. As you prepare to surrender to sleep, let these final thoughts settle over you like a gentle blanket. You live on a spinning ball of rock and metal, covered in water and air, orbiting a star, located in a galaxy, moving through an expanding universe. The spin of that ball creates the rhythm of your days, the cycle of seasons, the protection from radiation that allows you to exist. It is a gift from the ancient processes that formed our solar system, maintained by the fundamental laws of physics that govern all motion. It will continue long after you, long after humanity, long after complex life on Earth has ended and new forms have emerged. The universe is vast and strange, full of wonders we can barely imagine. Earth, with its rotation and its life and its complexity, is one such wonder, neither unique nor common, neither eternal nor fleeting, but temporary and precious, a place in space and time where conditions happen to be just right for creatures like us to exist, to wonder, to explore with thought and imagination what might be different. For now, Earth spins on, day following night, following day, in an endless cycle that has continued for billions of years and will continue for billions more. Sleep now, secure in that knowledge, and dream of spinning worlds and the forces that shape them. If you enjoyed this deep dive into hypothetical astronomy and physics, please consider liking this video and subscribing to Nebula Nights for more explorations of cosmic phenomena. Hit that notification bell so you never miss our journeys through space, time, and the fascinating what-ifs of science. Until next time, sleep well and dream of the spinning cosmos.